Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows of ISR Berhampur. I am the TA of this course named A Study Guide in Organic Retrosynthesis and Problem Solving Approach. So here I usually discuss about some questions based on different organic reactions like the name reactions and different type of functional group transformations and reactions, so which may help you to plan a retrosynthesis of any compound. So in the previous classes I have already discussed about that oxidation reaction, reduction reactions followed by oleifinations, then some reaction of double bonds also, and also some name reactions. So today I will continue the reactions of olefins. Then I think after one more class will be completed with all these important reactions. So we have already discussed all these name reactions and this olefination reaction. This reaction is remaining, that is Corey-Fuchs reaction. All these reactions here are used to synthesize a double bond, to synthesize a double bond. Synthesize a double bond. Now, what is the procedure, or what is the how we can prepare a triple bond from a ketone? How we can prepare a triple bond from a ketone? That is called Corey-Fuchs reaction. So this is one of the important reaction for any molecule synthesis, because by this reaction in a single step you can generate a triple bond directly from a aldehyde. So this is called Corey-Fuchs reaction, is designed to synthesize alkyne from aldehyde. So how this, if you add this, you know about this reagent. In case of apple reaction we usually use this reagent. So if in presence of CBr4 and PPH3, if you added in aldehyde, it will generate this alkene. After that, if you add butyl lithium followed by water, it will give us our alkyne. So this is the mechanism. if you see what is the step by step, in the first step, this alkyl bromide will react with PPST to form. This PPST will attack to this one of the bromine atom and it will generate this carbon ion. After that, through alpha elimination of one bromine atom, it will generate this carbene. The alpha elimination of this, it will generate this carbene type of system. Then it will react with our aldehyde and form this cyclobutane and butane type of intermediate, and through ring cleavage it will form this bromoalkene. Further, if you add butyl lithium on this, butyl lithium will attack to one of the bromine atom and it will be eliminated through generation of this alkyne in the system. Now instead of water, if you use a deuterated solvent, deuterium will be incorporated in this triple bond. Okay. Now let's solve this question. So we have to synthesize this compound from this starting material. We have to synthesize this product from this starting material using one of this, using Corey-Fuchs reaction in one of the steps. So this is a multi-step reaction. We have to get the so see what is the difference between the substrate and product and what functional group we have to change or we have to incorporate. So here if you see, this backbone is same, so only this aldehyde center has been converted to a alkyne with one carbon extension, and this ester has converted to a alcohol. So from this thing you can get an idea, okay, we have to perform some reaction so that aldehyde will be converted to alkyne and this ester will be converted to alcohol. So whenever you will see that aldehyde has been converted to alkyne, that means it is a Corey-Fuchs reaction. So if you perform the Corey-Fuchs reaction on it using CBr4, and PPS3, the next step we use butyl lithium and water. It will give us alkyne. Now in the next step only the ester has been hydrolyzed. So for ester hydrolysis, which type of reagent we usually use, we have already discussed. See, this is way to get an idea how to synthesize a large molecule. You have to know all the small organic reaction, otherwise you can't plan. So what will be the reagent required for hydrolysis of ester? If you use LiLH4, LiLH4 is used to for the LiLH4 has been used for reduction of aldehyde and ketone. If you use NaBH4, that is specifically for aldehydes. If I use BH3SMA2, that is specifically used for acids. So for ester, which is more suitable reducing agent, which will not hamper this double bond or this triple bond, that will be divalent. So you have to consider a reagent such a way that other functional group has been unaltered by this reagent. So if we add divalage as a solvent, if you use TCM, and so it will give us this alcohol. Okay. Now this is a question from the whatever we have discussed in the last class, that is a olefination reaction. These questions has been come in one of the previous year NET or GATE examinations. So I thought I will include this. This is from previous year NET or GATE, I don't remember. I think it's GATE question. So what will be the answer of this? So from silicon, this is the olefination reaction, and there is a so this type of, whenever there is a silicon and there is a fluorine atom is given, so it will undergo the elimination type of reaction. So this, it will attack to this silicon atom, this bond comes here, so it will give us a benzene. After that, if it react, sorry, 1 second. So from the product you have to get an idea. Here the reaction will not go directly, because if it is go through a benzene, there will be a formation of a new 6-member ring, but there is no formation of a new 6-member ring. Just a phenyl has been added to this group. Just a phenyl has been added to this group. So this reaction will not generate an alkyne, but from the product you have to get an idea also. So if there is a there is a benzylic double bond, so it will act as a nucleophile and attack to this, and this will open up. Generation of a positive charge here, and generation of a negative charge here due to opening of the benzene bond. Now if there is a proton at this place, so it will take a proton and to neutralize this positive charge. The driving force of taking up the proton, because the newly generated double bond is conjugated with both the phenyl group. This is the probability. Another probability, because we have to see that product is there or not. There is no such product like this. So there is another probability. If we take a proton from at this, there is a proton here also to neutralize this positive charge. So if you take proton from here, then product form is
তো বলবে যে খাবো কোনটা খাবো করলাম খাবো করেছি
so. Can you find this? So there is only two probability. Okay, we have to need to neutralize this positive charge. You have to take a proton adjacent to the positive charge. So proton can be taken up from here or here, but in the options there is no such product like this. So we have to take a proton from this blue marked proton. We have to take this one. So the correct option will be this one, option A. So the correct option is option A. Nilufa, can you please mute yourself? So what will be the product in this reaction? This is also an example of Corey-Fuchs reaction. What will be the product in this reaction? So from the Corey-Fuchs reaction, if how can you know that this is Corey? Whenever there is a reagent like CBr4 and PPS3 and aldehyde is given, that will be Corey-Fuchs reaction. Means the reagents will be same. If there is alcohol, that means it is a apple reaction. But if there is a aldehyde, this is the Corey-Fuchs reaction. So try to reconnect with all the reactions so that it will help you to remember all the named reactions and how they are different from each other. Apple reaction I have already discussed in one of my previous class. So if you add this reagent, it will generate an alkyne here. Sorry. It will generate a bromoalkene here, because the alkyne generated after the addition of butyl lithium. So in the first step there is no butyl lithium, so we will stop this at this bromoalkene step. After that they have added butyl lithium. They have added this butyl lithium, so it will give butyl lithium and water. Both of them will give us our alkyne. Our alkyne with a terminal alkyne with a hydrogen. Now in the next steps, if you add butyl lithium and this methyl chloroformate, methyl chloroacetate, then what will happen? It will take a proton from here, take a proton from here and generate a negative charge here. After that, this negative charge will attack to this carbon. This negative charge will attack to this carbon center and release this Cl minus from the system, generating this as our product. Okay, I hope it's clear. What will be the product in this step? This is also based on what we have discussed in the last class. As we discussed, if you use a sulfoniumylide, it will give a epoxide from a ketone. But if you use a sulfoxide and use a alpha beta unsaturated ketone, it will react with the double bond and give us a alkene. Cyclopropane. It will give us a cyclopropane. So the ketone here is a alpha beta unsaturated ketone. This is alpha beta unsaturated ketone. So if you add sulfoniumylide, this is called sulfoniumylide and this is called sulfoxoniumylide. So if you add sulfoniumylide, it will react with the carbonyl center and give a epoxide. So it will give a epoxide. So which one has given a epoxide in P? So this has given a epoxide. So and if you use alpoxoniumylide, it will give a cyclopropane ring. So the correct option is option B. Correct option is option B. All this mechanism and how the selectivity works, I have already discussed in the last class. You can go and check here. We are just exercising the problems, how they come in our upcoming examinations. So this is from a silicon type of compound, we are getting alkene. So this is a olefination reaction. So, okay. So this is a olefination reaction because we are getting a olefin. Now from as silicon is given, whenever there is a silicon based compound react to give us a alkene, that means is going through a Peterson olefination. That means it may go through a Peterson olefination. So if you see, and Peterson olefination are two types. One is base catalyzed and one is an acid catalyzed. We have already discussed about all this. So whenever there is a base catalyzed reaction, the reaction goes through a scene elimination procedure. And if it is an acid catalyzed reaction, the reaction goes through a anti-elimination type of procedure. So if you see the substrate here, they have not mentioned the stereochemistry of this bond. So we have to determine what is the stereochemistry of the bonds so that we can get this as our alkene. So this is a kind of retrosynthesis because here we know the product, but we have to determine the stereochemistry of the substrate. So if you don't know how the Peterson olefination takes place, you can't plan the retrosynthesis of this compound and how the stereochemistry has been maintained during the selectivity of the reaction, because this reaction is acid catalyzed. This is a Lewis acid. This is the Lewis acid. So in presence of Lewis acid, obviously this reaction will goes through a anti-elimination pathway. So our product is this one. I am just mentioning this as a R and R dash, and this is our methyl. Now to get this, we keep both R and R dash in the same way, and methyl here. The silicon and the oxygen should be anti to each other. Should be anti to each other. Now this is not written as like this way. So here in the substrate both these R group are not in the same plane, so it is kind of rotated. So let's try to draw it as the substrate. So if you just rotate this, this R group shifts this way. And this, sorry, due to rotation, this OH group comes to this above the plane and methyl goes to the below the plane. And this is silicon. So here, if you see what is the correct option, so the correct option is option A. The correct option is option A. Okay, so this is how, because we have to get the selectivity of anti-elimination, so we have to keep the OH and silicon anti to each other. So here in the substrate we just kept the silicon and OH anti to each other. How this is anti? Because as this showed as a flying wedge model, so in the flying wedge model we have kept this silicon in the above plane and OH in the below. So that's why they are anti to each other. Now as in the substrate these R groups are anti to each other, so you have to keep, but in the product these two are in the same side, so to get a similarity with the substrate we have to keep this away from each other, and due to that there is a rotation of this single bond, this carbon single bond. So due to this we are keeping this center fixed. Just imagine this as we are just keeping this center as a fixed. Now we are just rotating this carbon bond. We are just rotating this carbon bond. So that's why this methyl goes to the below the plane and OH goes to the above the plane, and we will get this. So the correct option is option A. Now we have already discussed some of the reactions of olefins like the Corey-Chakosky reaction and Simon-Smith reaction. There are some other important reactions which we will try to discuss today one by one, which will help you to get an idea how to plan a retrosynthesis of any compound. So first one is Limix Johnson oxidation, ozonolysis, hydroxylation, dihydroxylation, reduction and epoxidation. So first is Limix Johnson oxidation. The Limix Johnson oxidation or the Malapride Limix Johnson oxidation is a chemical reaction in which an olefin undergoes the oxidative cleavage to form two aldehyde and ketone units. The reaction proceeds in a two-step manner, beginning from a dihydroxylation of an alkene by osmium tetroxide, followed by a Malapride reaction to cleave the diol using periodate, and the periodate also served to regenerate the osmium tetroxide. So if you use this alkene and add osmium tetroxide, it undergoes a dihydroxylation, and if you add NiIO4, it undergoes a cleavage and give us these aldehydes. And it will give us this aldehyde. So next is ozonolysis reaction. So this is an organic reaction where an unsaturated bond cleaved by ozone to give a carbon-carbon. The carbon molecule bond is replaced by carbonyl groups such as aldehyde and ketone or carboxylic acid. So if you imagine this double bond, if you just cleave this along this, it will give us two carbonyl compounds. Now if the ozonolysis is take place in presence of zinc, DMS or PPS3, we can get aldehyde, but if it is in absence of zinc, so it will give us acid, and if there is any reducing reagents are given, it will give a reduced product. If any oxidation reaction is given, it will give us the oxidized product. Okay. Next topic is hydroxylation. So hydroxylation can be taken place in two ways. First one is hydroboration followed by oxidation, and next one is oxymercuration followed by demercuration. So how this hydroboration followed by oxidation take place? So if you use this double bond and add hydro and it will undergo the hydroboration, the less bulky center will take a boron, and the more bulky center will take more crowded center will take a proton and give us this hydroborated product. After that, if you add NaOH and H2O2, the carbon boron bond breaks up and form a carbon oxygen bond. During the course of the reaction, the stereochemistry is preserved, means if the hydroboration takes place through a chain addition, the boron and the hydrogen is added through a chain manner, and while this hydroxylation or this oxidation step, the stereochemistry is preserved, like whichever plane the boron has been added, the OH will be added to the same plane, because there is no such conversion along this center. The reaction is taking place on the boron. Next is oxymercuration and demercuration. So this is also a procedure for hydroxylation of double bond. In this case, if you add this mercuric acetate, it undergoes a addition along this double bond, and in the second step, if you add NaBH4, the carbon mercury bond is replaced with the hydrogen atom. This is replaced with a hydrogen atom. So can you what will be the reagent to generate this from this substrate? We have learned two hydroxylation procedure. One is hydroboration followed by oxidation, and another is oxymercuration followed by demercuration. Now to get this one from this, what reagent we have to use? So we have to see the regio selectivity of these two reactions. During this hydroboration and oxidation reaction, the boron is entered to the bulkier side, whereas hydrogen is added to the less bulkier side, and then carbon boron bond is replaced with a carbon oxygen bond. But in this case, it goes through a cyclic transition state, so it forms a cyclic cationic type of compound. Okay, now suppose it has a R group here. So among these two centers, which one is less bulkier? Obviously this center is less bulkier. So the next water molecule will attack to the less bulkier center. So water is added to this center, whereas in the second step if you add NaBH4, this carbon mercury bond is replaced with a carbon hydrogen bond. So from these two, what the idea we got, in case of hydroboration followed by oxidation, the OH group enters to the bulkier carbon, whereas in this case the OH group enters to the less bulkier carbon. So in from what is the difference between, so there is a hydroxylation take place. Now the OH group enters to this carbon. So among this C1 and C2, which one is bulkier or the sterically crowded? Which one is more sterically crowded? Obviously this center. So as we said, in case of oxymercuration and demercuration reaction, the OH group enters to the more bulkier side, whereas in case of hydroboration, the OH group enters at the less bulkier side. Okay. So in this case the reagent will be reagent will be this reagent of oxymercuration and demercuration. Okay. Now what will be the product in this case? So let's go first. It will form a cyclic cation. So if you add the Hg+2, it will form after that? After that, water is given. So water will attack to this center. This will open up. The next step, after that, as this is the enolic OH, so it will undergo the tautomerization. So it will form this ketone as our product. Okay, let's go to the alkene into neutral alcohol. In oxymercurination reaction, the alkene reacts with the mercuric acetate in aqueous solution to yield the addition of acetoxymercury group and hydroxy group across the double bond. And after hydrogenation reduction reaction, this mercury can be replaced with a H. So as this reaction goes through a concerted type of pathway, no carbocation is formed and the reaction follows the Markovnikov rule. So here I have shown the schematic diagram. If you see the mechanism, first this double bond undergoes a cyclic intermediate formation. After that, this OH water will attack and this three-membered ring will open up, and if you add any hydride source into this, then this Hg get replaced with that, forming this hydroxylated product. So based on that, there is various question has been seen in previous year NET and GATE examination. So I have gathered some of them. Let's solve one by one. The major product formed in the following reaction sequence. What will be the major product formed in the following reaction sequence? So as we have seen from the mechanism, so this triple bond will form a mercury cyclic intermediate with this mercuric acetate. Now instead of water they have given benzyl amine. Instead of water they have given benzyl amine. So benzyl amine can attack to this cyclic transition state and it will open up. Then the question is, which center the benzyl amine will attack, from this center or this center? So as we have learned that this always follows the Markovnikov rule. According to Markovnikov rule, the center containing more hydrogen will always get the hydrogen. So it will follow the Markovnikov rule. Therefore, this benzyl amine will attack here, so that it will open up and this center will be vacant for hydrogenation, and hydrogen will go to that center which is already rich in hydrogen. So it will attack here, this benzyl amine. After that, this amine will attack to this carbonyl center. Then there will be elimination of water. Generating a double bond here. And to gain aromaticity, this proton comes here and this goes here. So the correct option is option D. Okay. Understood? Let's go to the next question. This is also based on the same concept. I just give 5 seconds. Just solve by yourself. I just give 5 seconds. The major product of the following reaction is, so let's go step by step. As you know that mercury will be added here and H will be added here. Sorry, OH, as OH is given, so OH will be added here. I am just jumping the step, okay? Till I think you have understood how I have gone through. As it follows the Markovnikov rule, so obviously the OH will go where the number of hydrogen is less. So OH will attack here and mercury will attack here. After that, if you NaBH4 will add it, this bond cleave and we will get this as our product. So the correct option is option C. Oh sorry, not option C. Then now as NaBH4 will not only reduce this carbon mercury bond, it will also reduce our ester group. So in presence of ester, this will attack here and this open up. So the correct option is option D. Correct option is option D. Okay, understood. Only this center will not attack, right? Because all this hydrate source and also a OH minus is provided. So this that will open up this ester and forms the alcohol in the same medium, reaction medium. So correct option is option D. So this is your, sir, just note it down. Let's go to the next question. This is also based on the same topic. Here you can see in the back to back year we have got question from this oxymercuration, demercuration. So double bond is there. So there will be a Hg. So let's go from the scratch. So first this mercury cyclic transition state will form. The next step, as instead of water they have given methanol, so methanol will attack. Now the question is methanol will attack here or here? Here there is both the carbon is contain same number of hydrogen, so from the basis the count of hydrogen will not make a difference. So you have to consider the stability of the carbocation. So if you open up this one, there will be generation of carbocation here which gets stabilized by the Flassard effect of the adjacent oxygen atom. Because of that, this methanol will attack at this place, forming a OMe bond here, and NaBH4 is added which will replace this mercury bond with the hydrogen bond. So the correct option will be between this C or D. So A and B are already cut. So A and B are already cut. Next is they have given acetone. So this acetone will will bind with this through a kind of ketal formation. Now you always know that ketone always prefers the formation of 5-member ring, whereas 6-member ring. So in this case, these two OH will attack. The ketone always favors the formation of 6-member ring. So here, if you attack here, there will be formation of 5-member ring. But if these two OH reacts, it will be a formation of 6-member ring. So this reaction this the correct option is option C. It will be simple, just ketal formation, where the aldehyde protection type of reaction. Okay. So this is your answer. Just note it down. Let's go to our next question. What will be the major product A and B of the following reaction sequence? So on this same concept, this in presence of PPS3, in diazo will get reduced to form this NH2. Now in presence of CbZCl, this NH2 will be protected. So CbZ is benzyl, carboxybenzyl okay. After that, what will happen? They have given this Hg acetate, so it will form this Hg cation. This will attack here and will open up, forming this 5-member ring. Now this is already above the plane, so it will attack from the above the plane. So this both bond will be from the above the plane. And after that, this carbon Hg bond gets cleaved by this NaBH4 and form this as our product. Okay, so the correct option will be option D. So correct option will be option D. This is your answer. Next one. What will be the major product formed in the following reaction sequence? So what will be the major product formed in the following reaction sequence? So first they have added H3O plus. So H3O, in presence of H3O plus, this OH will be protonated. in presence of H3O plus, it will take a proton from here and it will be protonated and removed from the system, generating a carbocation here. So there will be generation of carbocation. After that it undergoes a 1,2 methyl shift. As there is a proton here, it will be eliminated to neutralize the positive charge. After that, if you add osmium tetroxide, it will undergo a dihydroxylation. Now if you use NaIO4, what will happen? So in presence of NaIO4, it undergoes a Limix reaction, which we have already discussed, this Limix-Johnson reaction. So it will undergo a cleavage. Cleavage of this double bond, the single bond, and generation of a 2 carbonyl center. Okay, so the correct option is option 3. Correct option is option 3. Identify the product from the following reaction. So we have already discussed about hydroboration and oxidation. This is based on that. I'll just give 1 minute. Just think what will be the answer. So this will undergo a hydroboration reaction. So hydroboration reaction, the OH will be in the less bulkier side and H will be at the more bulkier side. Now but we have to draw this in this cyclohexane manner. So let's so H will be here. There's a methyl group. The one probability is H is coming from and OH will be above. Both H and OH both should be above the plane. One probability is this. Another is H and OH both are in the below the plane. Another probability is this one. So you have to find which type of product we have. So H and OH both are above the plane. So our correct option is option A. So the correct option is option A. So this is our correct option is option A. What will be the major product form in the following reaction sequence? So what will be the major product form in the following reaction sequence? So from the mercury you can get an idea, it will go through a oxymercuration followed by demercuration. So in the oxymercuration demercuration step, first it will undergo the cyclic transition state, then this methanol will attack, so it will form a cyclic transition state like this. Now methanol will attack. Now among these two, if carbocation generated at this step, it is stabilized by the oxygen atom, and if the carbocation is generated here, it is just stabilized by the plus I effect of this carbon-carbon bond. So obviously the oxygen resonance effect is more than that of the plus I effect of this carbon-carbon bond. So the ring will be cleaved at this plane and methanol will attack to this side. So the methanol will be adjacent to oxygen atom. So the correct option is formation of this one. So this has been given in the options. This is A. This is C. So this methanol just adjacent to the oxygen is in the C and D. The product should be between C and D. Now in the next step they have given ketone, that is acetone and HCl. So here there is 3 OH. So one of the 2 OH will be protected. Always remember, whenever there is a ketone is given, it will form a 5-member ring, and if aldehyde is given, it will form a 6-member ring for carbohydrate system. If there is a ketone is given, then OH will be protected in such a way that it will give a 5-member ring, whereas that is a furanose ring. But if it give a aldehyde, it will give a pyranose ring, that is a 6-member ring. So the correct option is option D, because it's giving a 5-member ring. Okay. Provide the appropriate reagent to carry out each of the reaction. So you have to get this A and B. What will be the A and B? So to get this alkene from this alkyl bromide, it should undergo the elimination reaction. So as between H2SO4 will not be given because there is no OH is there. So for elimination of bromine, H2SO4 is not the good reagent. So option B is already cut. KMnO4 is not possible because to elimination of bromine, KMnO4 is not given. So the options are between tertiary butoxide or methoxide. So between tertiary butoxide or methoxide, tertiary butoxide is a good base than that of methoxide due to bulky size. So this will be our good, because tertiary butoxide is a good base, and for elimination we need a good base, not a good nucleophile. Methoxide is a good nucleophile, but tertiary butoxide is a good base due to its bulky size. So that will take a proton from at this place. It will take a proton from here, and this bromine will be eliminated, generating a double bond here. After that it undergoes a dihydroxylation. So obviously the osmium tetroxide. So this is undergoes the osmium tetroxide dihydroxylation. So the correct option is option A. What will be, how can we synthesize this product from this alkyl bromide? So they have just mentioned it will be 3 steps. It will be 3 steps. So here this part is already in this product, okay, up to this part. All this whole part is incorporated. So that is a possibility. How can incorporate this one? So if you just take a alkyne, like this, and add NaOH base, so this base will take a proton from here and generate a nucleophile at this center, and this negative charge will attack to this carbon atom and eliminate the bromine. So this is our first step. In the next step, if you just undergoes a reduction by using Lindlar catalyst, that is undergoes a partial reduction of the triple bond. If you add Lindlar catalyst and H2, it will undergo the partial reduction, and Lindlar catalyst reduction is always seen in manner, so it will give a syn double bond. It will give us a syn double bond. Whereas if you add the Simon-Smith reagent. It will form a cyclopropane and we'll get this as our product. Okay. Consider the reaction sequence below. What will be the X and P? What will be the X and P? So from the first step you can see it undergoing the double bond react to give a syn OH and OTS. That means somehow if you synthesize a dihydroxylation in a syn manner, one of the OH can be tosylated, so it will undergo the dihydroxylation, syn dihydroxylation. So which reagents you have to use between chromium trioxide, osmium tetroxide, NaIO4 and MCPBA followed by NaOH. This is already this is a oxidation reaction. Osmium tetroxide give us a syn dihydroxylation. NaIO4 is not for dihydroxylation step. If you use MCPBA followed by NaOH, MCPBA will give us a epoxide first, and if you add NaOH it will be open up and give a dihydroxylation. But the same is in this case we will get a anti-alcohol. In this case we will get a anti-OH. The two means two OH will be anti to each other. But in case of osmium tetroxide we will get syn hydroxylation. So there will be two OH will be syn to each other. So the correct option is osmium tetroxide. So osmium tetroxide, then they have added tosyl chloride and pyridine. So one of the OH get tosylated. The next step they are adding this tertiary butoxide. What will happen to this product? So tertiary butoxide, there is a proton here and it's a leaving group. It can be considered as a leaving group, and tertiary butoxide considered as a base. So it will undergo the elimination, the base, good base. So there is no question of substitution. OTS is a good leaving group. OTS is a good leaving group. OTS is a good leaving group, but as tertiary butoxide is a good base, because of that no substitution will take place, that just it will be a elimination. Now to eliminate this OTS there should be an anti bond to each other, anti-periplanar bond. Now there is one option is the elimination of the proton here, which is or elimination of this bond, because this bond is anti to this OTS. So in this case it will undergo the assisted type. So if you just draw this in a cyclohexane manner, it will give a better idea to imagine the anti-periplanar arrangement. So OH is here, and OTS is here. Now see, these two bonds are anti to each other. These two bonds are anti to each other. More than this H. More than this H, these two bonds are anti to each other. Because of that, the base will take a proton from here. So the correct option is there is a 7-member and a 5-member ring. There is only option. So the correct option is option D. Correct option is option D. What will be the correct sequence of the reagent to get A as the major product? So So what will be the correct sequence? In the all the 4 options, the same reagents are given, but the sequence is different. So to plan a retrosynthesis of any compound, the sequence is also important. We have to suppose we are performing multiple reactions. Now if you have to perform oxidation, reduction or substitution or something, which step will be performed first and which will be performed second, that we have to choose also. Because suppose you are adding any functional group in a first step and you are performing such a reaction in the second step where the functional group itself will react, so then that will be not a good for your reaction. So in the 4 options, all the reagents are same, but the recipients are different. So let's try. Let's first determine the changes. Here the OH group is converted to a OTR. So that means this TR group will be incorporated to this OH. Then this 2 syn OH has been protected to give a ketone, and this OH is oxidized to ketone. So the 3 reactions should be done. 3 reactions should be done. One is protection of this OH group, second is protection of this di-OH group, and third one is oxidation. So let's, if you give the dihydroxylation in the first step, there is a multiple OH are there. One is this one, and as this is 1 carbon extended, so this can rotate it. So one probability is these 2 OH can also react. So to specifically react these 2 OH, we have to protect this alkyl OH first. So first we will protect this one with TR. So first is protection of, first we will react, if we mention this A, B and C. So first we have to react the A center, second we have to react the C center, and third always place the oxidation in the last step, because if you keep the oxidation in the first in the middle step, it can protonate this OH and it can be eliminated. So then the third step will be B. So let's see, if you want to protect the TRCl will be needed. So in the first step TRCl, so options will be between 2 and 3. In the second step we want to protect this 2 syn OH. For this one we need this 2,2-dimethoxypropane. And if you use desmartine and para-adenine, it will oxidize the OH group to ketone. So the correct option is option 2. Option 2. The correct option is option 2. Okay. So this much for today's class. We'll meet you in the next class. Thank you. I'll just give an overview or last time for whatever we have discussed today. So we have discussed different type of olefination reaction in the last class. So we have incorporated another one, that is Corey-Fuchs reaction to generate an alkyne. We solved some question based on that. Then we solved some question to synthesize alkene. Then we read some question based on the reactions of double bonds and the selectivity, how we can get a hydroxylated product from alkene, and 2 types of hydroxylation by changing the reagents. If you perform the NABH4 the hydroboration followed by oxidation reaction, the OH group will be incorporated in the less bulkier side. But if you do an oxymercuration followed by demercuration, OH group will be entered in the more bulkier side. So we solved some question based on that also. Then some planning of retrosynthesis where the substrate and product was given. So this much. Thank you.